Hello, I'm Marcos Jimenez, and I'm going to start today with the 5th section of the Wave Phenomena 2 course, continuation of the previous section where we studied reflection, refraction, and diffraction. We are going to continue with the other 3 characteristic phenomena: polarization, Doppler effect, and wave superposition. The first lesson of this 21st section of the course is polarization, which we are going to develop according to the headings detailed here, starting with types of polarization, where I will also explain what polarization is by comparing it with a wave that is not yet polarized. This is a wave that is not yet polarized, a normal wave in certain circumstances that you can imagine as if it were a gymnast doing a ribbon exercise, a rhythmic gymnastic one, and she has her hand on the end of that yellow ribbon closest to us in perspective, and she's moving her hand according to that strange trajectory that you see there that includes even a little curl. And that trajectory or that perturbation is traveling along the rope so that each point does exactly the same thing as the previous one, just a little bit later out of phase, which is typically a wave-like process. Well, this wave of which we are seeing its vertical and horizontal projections on the back walls and on the ground, well, it has no specific relationship between the two components. It has nothing characteristic. It is an unpolarized wave. How can a wave be polarized? Here we have a first example. What is known as an elliptically polarized wave, in which any particle, any member of that wave, is moving along an ellipse. The gymnast's hand is doing it. It is moving along an ellipse with the end, and that movement is propagating towards the other parts. We are understanding here that there is no gravity and no losses, that it is a clean process. To simplify the visualization, obviously, okay, so then this elliptical polarization, all the particles move on ellipses, and the envelope of the whole tape at any time, the set of points that surrounds it, is that elliptical prism. As particular cases of this, we can consider the following. 1, that the two axes are equal in size, so that the ellipse becomes a circle. In that case, the trajectory of the gymnast's hand is a circle, and the motion of any particle is also a circle. In fact, it is like the previous one, with the difference that in this particular case, the axes are equal. Another particular case of ellipses, when one of the axes measures 0, so that I only have the other one left. And what I have is a straight line segment, so that the gymnast's hand moves, as we can see, along a straight line at the end. And that is propagating to the rest, and the whole wave is contained in a plane. It is said that this wave is linearly polarized. This is the case that we are going to deal with more usually in this lesson. Here, by way of summary of all this, we can see the 4 cases together. Especially notice the unpolarized wave, as it is clearly distinguished from the rest, which has specific geometrical characteristics. Which waves can be polarized? We already know that all kinds of waves can reflect, refract, have diffraction. Well, polarization is not a general phenomenon for any wave. It requires waves of certain characteristics. Here we are seeing how the tape reaches a wall, through which only one component remains. You can see on the wall in the background the vertical projection. As it is not affected through this kind of darker wall, the wave remains the same, while the horizontal part, the one you see on the ground, is suddenly eliminated. As a way of applying this, you can imagine that there is a vertical slit in the wall, so that the horizontal component of the movement of the tape cannot pass through, and only the vertical one remains. In this way, we are polarizing vertically, linearly, and specifically in vertical direction the tape. We can do it with any other direction by changing the orientation of the slit. Well, if we have a previously unpolarized wave that we were polarizing, the element that does this is known as a polarizer. What do we need for a wave to be polarized? First requirement, it must have a transverse part. A longitudinal wave like sound is not polarizable. Sound vibrates along the red line that we are seeing there, not perpendicular to it, and it would not be affected at all if there was any kind of polarizer. It would remain exactly the same. I need it to be a transverse wave, or transverse and longitudinal. The longitudinal part would not affect, the transverse part would. So it would also work with mixed waves. But it requires something else. As you can see in front of the polarizer, I have an unpolarized wave, and then it is already polarized. So what is the difference? That the polarized wave vibrates in only one direction. Before, when it was not polarized, it vibrated in the whole transverse plane. Therefore, to polarize a wave, I require that the non-polarized wave exists, that it vibrates in the whole plane. For example, the waves of the sea cannot be polarized, not because they are mixed of the longitudinal component, but we can try to polarize to transversal. It is that transversally they only vibrate vertically. They don't vibrate horizontally waves, And that way, I mean in the direction perpendicular to the propagation. And therefore, there is nothing to polarize. So what can we polarize? Well, now we will see some cases. At the moment, as I say, the ribbons of rhythmic gymnastics. As notation, we have said that the device that allows to pass from a non-polarized wave to a polarized one is called polarizer, and also the line that it respects, the line that it allows to propagate, is known as the transmission axis. Along the axis of transmission, the wave is maintained. In the perpendicular, we eliminate it. Apart, as I say, of this type of ribbon waves, what is a typical case? Well, we need a transverse wave that vibrates in the entire perpendicular plane, and the typical case is the electromagnetic wave, with all its particular cases, i.e. X-rays, gamma rays, colors, microwaves, radio waves. Here we are looking, for example, at an electromagnetic wave already polarized. The red arrows represent the electric field, the green arrows the magnetic field, which is perpendicular to the previous one. And this wave is said to be linearly and vertically polarized, because the direction in which the electric field vibrates is considered as a reference. How would a non-polarized electromagnetic wave be? For example, the electric field, instead of vibrating only up and down, would vibrate in the entire perpendicular plane, making any kind of trajectory, and the magnetic field accompanying it at 90 degrees. Well, this, as I say, is already a polarized wave, electromagnetic polarized, vertically in the case. And what happens if we use two polarizers? Here we have an example in which a non-polarized electromagnetic wave would arrive represented by crosshairs, that is, by a vibration both vertically and horizontally. The first polarizer arrives with a vertical transmission axis, so that it only passes, we see in the intermediate section, the components that pull you vertically. But what happens when we find the second polarizer? When we meet the second polarizer, depends on the orientation. For example, right now the transmission axes are perpendicular. The second polarizer has the horizontal transmission axis. The first one has vertical. It is said that they are crossed polarizers, so that if there were a non-polarized wave, the horizontal would pass through the second one. But as there is no horizontal, the horizontal that does not exist passes and continues not to exist, so no light passes to the other side, assuming ideal polarizers. The real ones do not cancel 100% of the components. What do we find if, on the contrary, the two polarizers have the axes approximately parallel? That as it arrives, it happens that the same light that crosses the first one would cross the second one, for other possibilities. Well, we can see that only the projection of the second of the intermediate polarized wave passes over the transmission axis of the second one. So the process we have is the one shown here. I'm going to do it now in front of me with these two polarizers. As you can see now, you are seeing my face, and now you are not seeing it so clear, because it is part of the light. Specifically, one of the components has disappeared. That is why you see me darker. However, that has not been affected by the second polarizer if I put it in parallel. You see that more or less you see me exactly the same intensity. But what happens if I now rotate one of them? You can see that you are seeing me worse and worse, and when I put them completely crossed, you will stop seeing me. You will stop seeing me. So we can play peekaboo like children, but instead of with my hands, I cover myself with a pair of polarizers. And I'm spinning. Let's see some additional examples. Here I have a mesh, and we can see how I place one of the polarizers, and we can see it darker. I also connect the second one, and you can see how it also looks darker in the area where one of them is. But in the area where both of them are, you can't see anything, unless obviously I change the transmission axis and I place them more parallel to each other. Other examples that we can see are, for example, detecting polarized lights. How do you know that a light is polarized? Because a non-polarized light, when it passes through a polarizer, it looks polarized, but a light that is already polarized when it passes through a polarizer, with the corresponding necessary addition, it is not seen as this calculator. Here you see the numbers. You see the numbers because there is light emitted, not by the numbers, by the background. The background of the screen is what emits light. And according to the direction in which you put this element, this polarizer, you can see that the background is seen, and therefore the numbers are distinguished, or the background does not pass the light it emits. And I do not see the numbers as contrast either. In other words, because this allows me to check that the light emitted by the calculator is polarized previously. The same happens with, for example, a tablet. Here I have a tablet, and you can see that there is a direction in which it propagates perfectly, and another one in which it doesn't travel, which shows that it is polarized light. You can also check this on your own if you have polarizers with, for example, computer screens, that exactly the same phenomenon occurs. Well, we continue with the explanation. and let's see how you can polarize a light wave. Light. There are 4 typical phenomena by which a wave can be polarized. The first one is by absorption. By absorption consists, for example, imagine that light arrives and we have a metallic grid, so that currents can be created in those metallic elements. So in this case, as the grid is arranged horizontally, when light arrives, the horizontal component causes an oscillation of the electrons of that grid, provokes an electric current, and that absorbs the corresponding energy. On the other hand, as there are no vertical conductors, it cannot absorb that energy and only the vertical part propagates. That is how polarizers like the one we have shown before work. In fact, what they have is that they are formed by very long molecules that by a manufacturing process are placed parallel to each other. And what happens is that when they are in the right direction, as they are all aligned, they absorb by electrical conduction inside those molecules the corresponding component, and that is how the polarizers work. The corresponding component. The key is that we need them to be as dense as the wavelength itself. For example, for microwaves. For microwaves that are centimeters, the wavelength is enough with a dense grid at centimeter level. For something that is a wavelength that goes between 400 and 700 nanometers, like visible light, that is the density of molecules that I need for a polarizer to work effectively. Second method, by reflection, it turns out that if a light bounces off an element separating into a reflected and refracted ray, the reflected ray is partly polarized and there is a certain angle of polarization. It's polarized and there is a certain angle for which it is completely polarized. You can see here that the reflected ray is completely polarized in the right part, and you might think, but the refracted one is not. Well, that is a question of energetics. I mean, as the reflected ray takes less energy than the refracted one, if the reflected one takes 10% of the horizontal and nothing of the vertical, then it is polarized. But on the other hand, for the refracted ray, it has 90% of the horizontal and 100 of the vertical. 90 to 100 ratio, it is not completely polarized, but partially polarized. By the way, the critical angle at which this occurs is quite curious. It occurs when the following geometry is given. This total polarization is when the reflected ray and the refracted ray are precisely perpendicular. At that moment is when the reflected ray is completely polarized. This, by the way, is used in things like glasses to avoid reflections in the snow or reflections in the sea when we go to the beach or when we are sailing. Polarization by scattering. This has to do with when, for example, the sun's rays arrive and meet the molecules of the atmosphere. A molecule of the atmosphere. Obviously, most of it passes between the empty space, but one meets a molecule, excites the atoms that are there that remit light, and they remit it in all directions in the perpendicular plane in which they have vibrated. This would be a polarized light that is incident, but if it is polarized light in the opposite direction, the vibration is different and the planes are different. So the question is, and the superposition, because here we have in the center the sum of the left part and the right part, you can see that the result when an unpolarized wave arrives is that the diffuse wave, the one that comes by dispersion, is polarized. And it happens, as we see here in the image on the right, that we have a day with clouds. We do not see where the sun is, but the light is polarized like this. We do not have the capacity, but there are animals like bees that do distinguish the polarization and see a pattern like this and say, I know where the sun is. Indeed, the clouds are gone. It was hiding there. The last phenomenon that has to do with all this is birefringence. Birefringence is characteristic of materials that have the property of having double speed of light. That is, the speed of light is not constant, but depends on the direction. That means that there are several refractive indices, and that the rays are broken into 2 parts. As we are seeing in this video, it turns out that they leave by 2 paths, and that is what makes these materials typically have double image. But what is not so usual is to know that they are images, that they are vibrations perpendicular to each other, that they are polarized, as in the example that we are going to show here. Where you can see the double image of the grid through the birefringent material. And to see that they are polarized, it is enough for me to put the element and see how, depending on the direction, I see both. I see one, or I see only the other one. I do it slowly, and then for that video where you consider more convenient to notice the phenomena. Well, because the example is finished, I put here the final index with which the lesson ends. Thank you very much for your attention.